So this is implicit differentiation. So what we're doing here is we're trying to differentiate something that has a y in it with respect to x. So basically the problem here is if you were going to differentiate like, let's say x squared, that's easy, yeah, because we know it's 2x. But what if we wanted to differentiate something like y squared? Well, the x's and the y's don't match up, so you can't do anything with this the way it is. What you really want this to be is d dy of y squared. These match up, and then that would be 2y. So that's cool. Now to do this, to get from here to here, there actually is a trick that we can use, and that trick is basically the chain rule. So what we do is we say, well, look, I've currently got d dx of y squared, yeah? I would prefer to have a d dy here. So what we do is we manufacture it. We say, okay, let's chuck a d dy here, but let's chuck a little y up here. So now this thing and this thing would cancel out, leaving us with what we had originally, which was d dx. So the reason that works is because you're basically making the chain rule that you want, which now means that this part we can do, it's 2y, but this part at the front is actually not anything that we do anything with. This is the y derivative, it's y dash, or we'd often just leave it as dy dx. So what we've got here is the derivative with respect to x of y squared is 2y, which makes sense for that bit, but then we have this part here and it's basically a correcting factor. So anytime you differentiate something with respect to something it's not in here, we multiply by this factor, correcting factor, dy dx. So I'll show you a few and then it'll make sense after we've done a few. They're all very, very similar. So we'll do the first one. It says, in each of the following find dy dx. Now we're going to use the chain rule here. So this is what we just did, what I just did with you. So I'm just going to move this up so I've got a bit more room. Okay, so we're going to look at differentiating. First thing you have to do is you have to show people what you're doing, which is you're differentiating both sides with respect to x, like that. Now we differentiate both sides. 2x. The problem here is this. This doesn't have an x in it. So we're going to differentiate with respect to x, which makes it, with respect to y, excuse me, which would make it just a 2, yeah? But because it wasn't an x, strictly speaking, we multiply by this correcting factor, which I'll do in a different colour, dy dx. On this side, derivative of a constant is 0. Now the whole idea with these questions is to find dy dx. So now you've actually done all of the calculus. Now there's a bit of algebra. We actually have to find dy dx. And we do that by just rearranging the equation. So I'm going to move this whole part over here to this side. And 2x on 2, which is x. So that means our derivative, dy dx, is just x for this question after all of that. The next one you've got here is a little bit harder. So you've got a derivative, d dx, of each side. And you can see here that you've got product rule because you've actually got two things multiplied together. On this side it's easy, derivative of 1 is just 0. So here we've actually got two things. I'm going to separate these into a u, which is x squared, and a v, which is y. Now we're going to differentiate both of these with respect to x. Yeah, I'm going to make the dash with respect to x. That's going to be 2x, that's all cool. Differentiating this with respect to x actually makes this not 1, because it's not an x there. It makes it 1 times dy dx. Because imagine if you were differentiating with respect to y, it'd just be 1. Cool bananas. But you're differentiating with respect to x. So you have this dy dx there. So now, cross multiply. X squared, this is just dy dx. Plus these two together, which is 2x times y. So now if we're trying to find what dy dx is, this is where we just rearrange. So we don't have to do any more calculus at this point. Looks like this, with a bit of cancelling. So that's dy dx. When do you use this method? You use it when x and y are basically tied up. So with something like this, you could have rearranged this and just got y in terms of x, yeah? If you'd done that, you would have ended up with, say for example, just do it at the bottom, you'd have had 2y equals x squared minus 3, which means that y equals a half x squared minus 3 on 2. When you differentiate, that goes away, 2 comes out the front, that goes away, it would be x. And that's why you have x over here. So you could have actually just rearranged the equation. And you know, sometimes that's easier, but in the case where x and y are tied up, you often can't do that. So that's why we have to use this idea of implicit differentiation. So the last one on this page, again, first thing we do is differentiate each side. Then what we do is we look at anything that has two things multiplied together, like this. So you might like to do this off to the side if you want to, or you could do it underneath. I'm actually going to do it underneath this time, so you can sort of see a different thing. So v is the y, u dash is 1, v dash is, remember that if you differentiated that it would be 1, but it's not x, so we have dy dx. So now let's do the differentiating on this thing. So that was just for this bit. So the derivative of x squared is 2x. The derivative of this part, there's a negative out the front. So now inside here it's going to be u dash v plus v dash u. So in this case we'll just use the bits we have, cross multiply, u dash v plus v dash u plus, now differentiating this it would be just 2y, yeah? But there's no x's in there, so we have this dy dx term equals, this side is just 0. So now you can see that when we expand this out, that negative goes all the way through there. You can see that we've got two terms that have dy dx. So we've actually done all the calculus is done at this point. This point that I'm going to do in purple is actually just all algebra. So it's all about getting your two terms. I'm probably just going to move these over, to be honest, to this other side and leave everything else. And then we've got to get a common denominator here. dy dx is common to both terms on the left side. Oops. So that means to finish this off, and I'll just move this up a little bit. So that's a little bit messy, but you can follow it. The last part of this would be to then get dy dx on its own. So that would be dy dx equals, take this stuff underneath and divide it through. So negative x plus 2y, like that. So what you've done here is you've actually done, first of all, the calculus, so differentiating this thing to 2x, this thing that became y plus x dy dx, and this thing that became 2y dy dx. Once you've got all the terms there, it's then a matter of finding dy dx, and that's by rearranging the equation and getting dy dx on its own. So, excuse me. We've got a few other ones here. So again, the same idea, we'll go through these pretty quick. So we've got, actually I might do these one on top of the other. So we've got y equals x squared e to the y. Two things here. I'm going to do quick product rule so you can see how to do that. So with quick product rule, what you do is differentiate one at a time. I'm going to tick the one I'm differentiating. So differentiate x squared, that's 2x, leave the other one, plus differentiate the other one. Now this would normally be just, imagine it was e to the x, yeah? It would just be e to the x. But because there's not an x up here, we multiply by dy dx. So that's the derivative. And then this one we actually then multiply by. So we basically differentiate them one at a time. So we differentiate, leave that one, differentiate, leave that one. So we now have 2x e to the y plus this one's x squared dy dx, e to the y, like that. Now the problem with this one is that you've got, on this side, I've done this as y dash, yeah? Now y dash can also be written as dy dx. So we've actually got some dy dx's everywhere, which means I'm going to get dy dx all on one side, because I ended up with a dy dx on the right side too. So I'm going to take these terms here over to this side. I'm now going to have dy dx that's common. I'm going to factor it out. 1 minus x squared e to the y. And then to finish it off, we get that on its own. So divide through by 1 minus x squared e to the y, like that. So it's a bit tricky, that one, because there's quite a few things going on. All right, with this one, let's move this over. So we're going to look for, again, this one's trig, so it's going to be a little bit tricky again, but that's cool. So we're going to differentiate both sides here. So derivative of cos squared x. Now, the other way of writing cos squared x that I think is a bit better, just for you to see what's going on, is that this is just a squared, like that, yeah? So you can think of it, it's a little bit easier to do chain rule. So derivative of sine y, normally that would be just cos y, yeah, but because it doesn't have an x, it's dy dx as well. Derivative of cos x squared is going to be 2 out the front, and then the derivative of the bracket, which is negative sine x, and then the bracket itself, and take it down by 1. All right. So what we've got now is we've got dy dx on the left side. We're going to rearrange, so we'll simplify this a little bit. So negative 2 sine x cos x on, and take the cos y underneath. Now you might like to change this into double angle formula. 2 sine x cos x is the same as sine of 2x. So you might see it written like that. Or you could just leave it there, it's totally fine. The last question on this page I've got here is find the equation of the tangent at the indicated point of the following. We'll just do the first one, which is A. So the equation of the tangent, remember the equation of the tangent is y equals mx plus c, where m is dy dx at that point. So first thing we're going to have to do is find dy dx. Now you can see that we've been given this equation here. So let's find dy dx first. Let's differentiate each side with respect to x. So d dx of each side. You can see differentiating the left side you get 2y dy dx because there's no x's in there. This becomes 8. So dy dx equals 8 on 2y, which equals 4 on y. Now we've actually been given a point here, which is the point 2, negative 4. So what we need to do is, first of all, I'd find the derivative at that point. Now, a nice way of writing this, if you'd like something kind of mathematical, is to say y equals negative 4, like that. And that says to people you're going to substitute y equals negative 4 into this. It's 4 on negative 4, which is negative 1. Now this thing here is m. Remember that this is the gradient. So for our tangent, y equals mx plus c, which is our tangent, we can now substitute in 3 different things, the y and x values, and m, hoping to then find what c is. So we'll put in the x and y, the y, and the m, which is negative 1. So we get negative 4 equals negative 2 plus c. So that means that c equals, that means that c equals negative 2. So therefore the tangent line is y equals m, which is negative 1, x, plus c, which is negative 2. So our tangent is this guy right here down the bottom, y equals negative x minus 2. That is the tangent at the point 2, negative 4 for this particular graph. Next one, we were asked to find the gradient of the curve. Gradient's easy because it's just dy dx. So again, with this one, we just straight up, it's at a point as well. So we'll have to find dy dx and then sub in the point. So first thing we're going to do is just differentiate each side. If it only has x's in it, the term that we're looking at, then it's just easy, just differentiate it. So this will become 3x squared, and this will be 3y squared, but with a dy dx, because it doesn't have any x's. This is 0. And we just rearrange this now. Dy dx on one side, take the x squared stuff over, and then we would divide by the 3y squared, which is negative x squared on y squared. Like that. So now you can see we've got a point here, so we need to substitute that in. So I'm going to actually say it x equals 1 and y equals 2, and sub those both into here. So x equals 1, y equals 2. And remember that the negative is not squared here, the negative comes from this part, so it's going to be negative 1 on 4. So the derivative of the gradient dy dx at that point of the curve is negative 1/4.